Imagine our sun, a giant ball of incandescent gas, occasionally unleashing bursts of energy so powerful they can disrupt our technological world. These bursts, known as solar flares, are sudden intense flashes of brightness on the sun's surface, representing the most powerful explosions in our solar system. Solar flares release tremendous amounts of energy, equivalent to millions of hydrogen bombs exploding simultaneously. This energy travels outward from the sun in the form of electromagnetic radiation, including X-rays and ultraviolet light. These bursts of radiation can reach Earth in minutes, affecting our atmosphere and technology. Understanding these solar flares is essential for protecting our technology-dependent society. From communication systems to power grids, our modern infrastructure is vulnerable to these solar storms. As we become more reliant on technology, predicting these events becomes even more critical. By studying solar flares, we gain insights into the complex and dynamic nature of our nearest star, the future of our technological world may depend on our ability to anticipate and mitigate the impacts of solar flares. The sun's magnetic field is a complex and dynamic entity. Generated by charge creates a swirling tapestry of magnetic field lines. These lines can become twisted, storing tremendous energy. When they reconnect, energy is released explosively. This process, called magnetic reconnection, drives solar flares. Energy converts to radiation, including X-rays and UV light. Flare intensity depends on stored energy. Solar flares often accompany coronal mass ejections, or CMEs. CMEs can cause geomagnetic storms and auroras on Earth. In 1859, the world witnessed the most powerful solar storm in recorded history, known as the Carrington Event. Named after Richard Carrington, this event showed the sun's power and its impact on Earth. Telegraph systems went haywire, sparking fires and delivering shocks to operators. The aurora borealis was visible as far south as Cuba and Hawaii. The night sky was illuminated with vibrant displays of color. If a similar event occurred today, the consequences could be severe. Our modern power grids and satellites are far more vulnerable. Satellites orbiting high above Earth are particularly vulnerable to the effects of solar flares. The intense radiation from these flares can damage sensitive electronic components, disrupting communications and navigation systems. Solar flares can also increase the density of the Earth's upper atmosphere, causing increased drag on satellites and potentially shortening their lifespan. The increased radiation from solar flares can interfere with radio signals, disrupting communication systems on Earth. This can affect everything from GPS navigation to satellite television broadcasts. The disruption of communication systems can have significant economic and social consequences. Engineers are developing radiation-hardened electronics and other protective measures to enhance the resilience of spacecraft. Understanding the dynamics of solar flares and their impact on the space environment is crucial for designing and operating robust satellite systems. Protecting these vital assets is a key challenge in space weather management. Power grids, the backbone of our modern society, are also susceptible to the effects of solar storms. Geomagnetically induced currents, or GICs, generated by fluctuations in Earth's magnetic field during solar storms, can flow through power lines, overloading transformers and causing widespread blackouts. A large-scale power outage caused by a solar storm could have cascading effects on other essential services, such as water supply, transportation, and health care. The interconnected nature of our modern infrastructure makes it particularly vulnerable to such disruptions. In 1989, a solar storm caused a major blackout in Quebec, Canada, leaving millions without power for hours. This event served as a stark reminder of the potential impact of solar storms on our power grids. Efforts are underway to enhance the resilience of power grids to solar storms, including developing protective measures for transformers and improving grid management strategies. Protecting solar power grids from the impacts of solar storms is a critical task for ensuring the stability of our modern society. Scientists are constantly monitoring the sun's activity, using a variety of instruments to observe solar flares and other solar phenomena. Space-based telescopes, such as the Solar Dynamics Observatory, provide continuous observations of the sun, allowing scientists to track the development of solar flares and other eruptive events. Ground-based observatories also play a crucial role in monitoring solar activity. By combining data from space-based and ground-based instruments, scientists can build a comprehensive picture of solar activity. Predicting solar flares is a challenging task, but significant progress has been made in recent years. Scientists are developing sophisticated computer models that can simulate the sun's magnetic field and predict the likelihood of solar flares. These forecasts are essential for mitigating the potential impacts of solar flares on our technology and infrastructure. Advanced warning of solar storms allow satellite operators, power grid managers, and other stakeholders to take protective measures. One of the most beautiful effects of solar flares is the aurora borealis and aurora australis, also known as the northern and southern lights. These displays are caused by charged particles from the sun interacting with Earth's magnetic field. As these particles return to their normal state, they emit light, creating the shimmering curtains of the aurora. Witnessing the aurora is a truly awe-inspiring experience, a reminder of the dynamic relationship between the sun and Earth. Solar flares don't just affect Earth, they impact the entire solar system. The radiation and charged particles emitted by solar flares can interact with the atmospheres and magnetic fields of other planets, moons, and even asteroids. On Mars, for example, solar flares can strip away the planet's thin atmosphere, contributing to its current dry and desolate state. The lack of a global magnetic field on Mars makes it particularly vulnerable to the effects of solar flares. The moons of Jupiter, particularly Io, also experience the effects of solar flares. Io, the most volcanically active body in the solar system, has a thin atmosphere that is constantly being bombarded by charged particles from Jupiter's magnetosphere and the Sun. Studying the effects of solar flares on other bodies in the solar system provides valuable insights into the processes that shape planetary environments. It helps us understand the diverse range of conditions found throughout our solar system and the role of solar activity in shaping these conditions. Solar flares, while beautiful and awe-inspiring, also pose a significant threat to our technologically dependent society. Understanding the nature of these solar storms and their potential impacts is crucial for mitigating the risks. Continued research and development of prediction capabilities are essential for protecting our critical infrastructure. As we become increasingly reliant on technology, our vulnerability to solar storms grows. Power grids, communication systems, and satellites are all susceptible to the disruptive effects of solar flares. International cooperation is essential for effectively addressing the challenge of space weather. Sharing data and expertise across borders is crucial for improving our understanding of solar flares and developing effective mitigation strategies. By continuing to explore the mysteries of solar flares, we can safeguard our planet and ensure a brighter future for generations to come.